Section 14.3 has the longest title of any section in the book, I think. It's awfully long anyway. The Pythagorean Theorem, the distance formula, and the equation of a circle. All of these three equations, formulas, if you will, are really the same thing. That's why they're showing up in the same section. So we'll kind of make connections back to each of them as we move through them. But the first one we're going to start with is the Pythagorean Theorem. So the Pythagorean Theorem says that if a right triangle has legs of lengths A and B and a hypotenuse of length C, then A squared plus B squared equals C squared. And there are hundreds of proofs of this. In fact, one of the proofs of this, I can't remember which one it is, I don't think it's any of the ones that's on the screen actually, was actually proved by a president of the United States. Does anybody have heard of who that president would be that proved a version who created a proof of the Pythagorean Theorem? It was President Garfield. So now you know. Yeah, it was President Garfield. The pictures at the bottom, of course, are not actually proofs because proofs involve words and arguments. But they are the pictures that sort of go along with the proofs. The one in the top right corner is the one that you see drawn a lot, the squares off of each side of the triangles themselves. But what you can actually see is some of the other pieces at the bottom. As you can look at the part one on the far right, for example, looking at that, you should be looking at that and think, well, there's got to be something with similar or with congruent triangles going on there, right? I see 4 congruent triangles around the outside. There's got to be something going on with that one. The one here in the middle, there must be something going on with the areas of the rectangles and things going on with that one, right? So there are hundreds of proofs of this particular formula. We're going to focus on the using of it today, okay? So, alrighty here. This is a not so straightforward example on purpose because I think you know how to do the straightforward examples of this particular theorem. There are how many right triangles in this picture? More. There are 3. There's the large one on the outside itself, and then there's the smaller ones on the left side and on the right side. Okay? So one of those 3 triangles, you know 2 of the sides for. Which one? The large one on the outside. So we're going to start with that particular triangle, and we're going to make connection to the fact then that we can find the third side of that triangle, which is the letter X. So what would be the equation? You got to make sure you set it up right. Right? The hypotenuse is the one that's alone. Which of those sides is the hypotenuse in this equation? X. Okay, the hypotenuse is the side opposite the right angle. The right angle is right here. So the opposite side is side length X. Remember, we're looking at the big outer triangle, not the smaller ones. What are the side lengths of this? 4 and 4 radical 3. The Pythagorean theorem says that each of the base lengths would be squared and then added together, and that will equal the hypotenuse squared. So 4 squared is what? 16. Good. What is 4 square root of 3 squared? Okay, and how did you get 48, Brendan? What did you do?
Well, I know that 4 squared is 16, and I know that the square root of 3 squared is 3.
Right. Okay, so we're squaring each of the pieces. We're allowed to do that. Basically, it's an operation that deals with that exponential, right? You can distribute the exponential to the 2 pieces that are inside because the 2 pieces inside are multiplied. Okay? All right, and then I've got x squared over here. And Brendan was right, that is 48. So what then is 16 plus 48? It is 64. So I've got x squared is equal to 64. What's x? 8. So I'd square root both sides, and we get 8. There's no units on it, so we're done. It's 8. Now, I use this example and the way it's structured on purpose because if you try next to use the Pythagorean theorem, you're going to fail. Because both the smaller triangles on the left and on the right, you only know one of their sides. You know the long side at the bottom, but that's not the whole side of either of those smaller triangles, right? It's their side plus some more. and you don't know how much. In other words, we don't know how to divide up that 8 along the bottom to make sure that it's done properly, correct? So what actually happens next is that you recognize, or you would want to recognize, that there are right triangles in this shape. And these right triangles share some common angles as well, correct? So let's just use the triangle. Let's see, which one did I use? I used the triangle on the right-hand side. This is the tiniest triangle here. So if I use this triangle over here, and I'll highlight them in, or box them in different colors. So here's the small triangle I'm talking about in red. And of course we have our larger outer triangle, and I'll do that one in blue. So our larger outer triangle, which I'm trying not to overlap them so we can see them clearly, is this one right here. They share an angle in common. What angle do they share? Nope, they don't share the 90-degree angle. Yeah, they share this angle. Whoops, let me get the color right. Or here, that'll work. They share this angle here at the bottom. Right, that angle is in both of those triangles. 100% exactly the same angle. And if it helps you to redraw them, the big outer triangle that I did in blue, I don't want to do it in blue because then you won't be able to see it, is right here. And we've got a right angle at the top, and we've got this angle that matches. And we have this little triangle over here with a right angle over here and this angle that matches. This is 4 square root of 3. This is 8. And this is y, or sorry, this is 4. This one's y. This one we don't know at the bottom. We don't even have a letter for it. And this one is 4. Okay. Because they have two congruent angles, that makes these pair of triangles similar. That's one of our similarity theorems. Two angles that are congruent makes a triangle similar. They might even be congruent. We know they're not because they're obviously not the same size. But it's at least enough to tell us that they're similar. Similar triangles have a corresponding ratio, right? The whole idea is that we could take all the sides of one of their triangles and like multiply them by something to get the other one. There's that ratio. So what we want to do is we want to set up a ratio of the side lengths. And they both have a side length in common that we know, that is the hypotenuse. Right? They both have a actual angle or a side length measure for the hypotenuse that we know. So I'm going to set up a ratio with them, and we'll put the hypotenuse. Do you want to put it on the top or on the bottom of our fraction? Top? Okay. So we're going to put our hypotenuse on the top, and we're going to put some other side, we'll call it a leg, on the bottom. So the hypotenuse on the top, which we'll just go from left to right since I've got them drawn that way. My first hypotenuse is 8. My second hypotenuse is 4. Okay, so we're setting up a proportion. And then we want to compare the legs. Well, we want to make sure that the leg that we're going to do the comparison of is the leg we want to find out about. That is to say, it's y. So in the smaller triangle, my leg y is what needs to go down here. The only thing that you really have to be careful of is to make sure that you get the right, that is the correct leg of the other triangle identified with that side y. So here's what I would suggest doing. In the little triangle, the side y, the leg y, is it the longer leg or the shorter leg? It's the longer leg, correct? So in my triangle on the left, which leg is longer? 4 radical 3 or 4? The 4 radical 3 is longer. Are you guys with me? So the 4 radical 3 will go on bottom. Oh, that's okay. These two correspond to each other because they are both the longer sides of the legs. How then do I solve for y? There's a couple of options truly. Cross multiply, which is the longer of the two options. Cancel, what do you mean by cancel? I think you're on the right track, but I don't think divide by 4 is what you meant to say. Reduce what? What do you want to reduce, Sally? The 8 and the 4 on the left-hand side? How will they reduce? Is that what you wanted to divide by? Okay, but we would divide not by 4, but, well, we could divide by 4. I don't think that's going to be especially helpful. How about we divide by 2? Can I show you why I want to divide by 2? I'm going to suggest we divide by 2, and let me show you why. If I divide this one by 2, what do I get? And if I divide this one by 2, what do I get? What's y? It's 2 radical 3. Because the other fraction's actually the exact same now on top, correct? These are equal. I just noticed them because it's double. You know, the one on the left is double on top of the one on the right. So that's why I wanted to divide by 2. You totally could divide by 4. You totally can cross multiply. There's lots of ways to solve the problem. Any and all of them are perfectly fine. No matter which way you do it, you're going to find the same y value, and it is 2 radical 3. You all right with that?
I don't know if I would have thought.
It's okay. The only reason that I thought of it is because this number was twice as much as this one. That was the comparison I saw.
So would an acceptable answer be 3.46?
It's a good question. It's an approximate answer, right? So it would depend on how the question was worded. If they don't tell you to approximate, we want to keep it exact. If it's a word problem with units on it, then yeah, I usually say go ahead and use the decimal, because if you tell somebody an answer that says, I need to measure out a side of a garden that's 2 radical 3, they're going to look at you like you just jumped off, you know, the crazy ship, right? They are. So it kind of depends on the context of the problem. So most of the times, like this particular problem, I would say leave it, because there's no units, there's no context, there's no nothing, and 2 radical 3 is exact. Okay? All right. What this is actually the converse to the Pythagorean theorem. Okay, so it means that it's the Pythagorean theorem backwards. It says, if a triangle has side lengths a, b, and c, where a squared plus b squared equals c squared, then in fact it is a right triangle. It's the same as the Pythagorean theorem, but the if and the then are switched. In other words, what that means is, well, it means we can do the next problem. Because the next problem actually wants to find out, if I give you 3 sides of a triangle, can you figure out if the triangle is a right triangle? And the answer is yes, you can. You just have to see whether or not it satisfies the a squared plus b squared equals c squared. Now, you do have to make sure as you're looking at these that you correctly identify which one is c. If this is a right triangle, which of those 3 values has to be c? 24. Why? Lauren, you were awfully quick to answer. Why?
Because C is going to be the longest side.
Right. Yeah, so the only way we can test this and make any sense of whether it works or not is to let where we're trying to see, let the C be the 24, the longest side. So we're testing to see, does 10 squared plus 16 squared equal, and I'm going to put a question mark because we don't know that they are, 24 squared. All right, I know you guys know what 10 squared is, so somebody tell me that one. 100. Does anybody know 16 squared? 256. If I had a piece of candy, I'd give it to you if you know 24 squared. Oh, I bet you looked in your calculator. 576. What is 100 plus 256? 356. Does 356 equal 576? No. Those are not equal, right? It's not equal. So we need to make sure we answer the question. The question asked us, can these numbers represent the lengths of a right triangle? And the answer is no, they cannot. They cannot answer. They cannot be the lengths of a right triangle.